Hello, period 8. Welcome to a very important class. This is like post FTC day. I know you have the and it's yeah. And it's how'd that go, by the way? Okay, good. What I would like to do for about a half an hour is go over some homework, and then we're going to learn something new, which is very interesting and exciting. So there are a couple things I wanted to do. Shall we do, let's go over this AP practice problems on the FTC packet first. I think that's a good, interesting problem. Can you take that out? There was this graph, and the graph looks something like this. So we're practicing two things here, kind of how to think about these problems and also how to do them by showing enough work and making enough quality explanations so that it makes sense.
Mr. Rose.
Yes.
For these questions, is there a difference between justify your answer and explain your reasoning?
Not really.
Okay.
Okay. So we have 5, -1, 2, 2, and then these are semicircles. And they tell you in the problem, so just so you don't have to guess, that this function is determined by semicircles and lines. Okay, another thing that's really important is that this is a graph of f prime. Bless you. So if you get that wrong, you know, kind of the entire problem is sort of destroyed. So then we have a whole bunch of questions which they ask you about the f function, and you're going to use this graph of the derivative to answer those questions to justify. Oh, there's one more really important piece of information, which is that f of 1 is 3. So given that this is the graph of f prime, and given that f of 1 is 3, and this is the derivative, let's start answering some questions now. So part A. Find all the places where f has a relative maximum. Okay, Josephine, where does f have a relative maximum? In general, for any function f, when does a function have a relative max?
Where the derivative is going increasing and then starts decreasing.
Okay, but you actually said the wrong words. I know that you know what you're talking about. Try it again. When does a function have a relative maximum?
F prime is like positive and then negative.
Okay, yes. That's different from what you said the first time, right? Yeah, that's exactly what we're looking for. F has a relative max when f prime change. I wouldn't write this down. I'm just writing. This is what you should be thinking in your brain. F has a relative max when f prime changes from positive to negative. And since you're looking at the graph of f prime right there, you know, then where does this happen?
X is -3.
X equals -3 and x equals 4.
That's it. That's all you have to do. So then what you should write on your paper, this is kind of like what you should be thinking in your head. What you have to write on your paper is f has a relative max at x equals -3 and x equals 4, because that's where f prime changes from positive to negative. Is everyone content with that explanation? And because they say justify your answer, that is code word for some kind of sentence required, or half sentence, or something like that. But this is sort of like the minimum that you have to write. And they're just basically testing. Do you know the first derivative test? And are you on the ball enough that you can abstract away from this individual problem? Okay, part B. Part B says, find all values at which f has a point of inflection. Well, let's just talk this one out now instead of writing it down. Where is a graph f going to have a point of inflection? Pure hope.
When f prime changes from positive to negative or negative to positive.
Yeah, basically where the sign of the second derivative changes.
Okay.
So in fact, maybe it might help to write that on your paper. So we're looking for points where f double prime changes sign. And where does f double prime change sign on this graph, or using this graph?
Where
Where
f prime has a relative extrema. Where f prime has relative extrema, which is at x equals -4 x equals 2 and x equals -1.
Yeah, so you're looking for places, in fact, if it helps you, you could even make kind of a sign chart for f double prime. So here is -5 and here's 5. Well, this is a graph of f prime. So over here, since the derivative of this curve is positive here, and therefore f double prime is positive on the interval from -5 to -4. But then, just like he said, at -4, now the slope of this graph is negative, and it stays negative until -1. But this is the slope of f prime, in other words, f double prime. So f double prime is negative from -4 to -1, and then the slope of this graph is positive until 2, and then the slope of this graph is negative again until 5. And so the answer is there's a point of inflection wherever the second derivative changes sign, which is essentially like the derivative of this graph. So, and that's all you have to write. F has a point of inflection at x equals -4,
-1
and x equals -1, and x equals 2. Because that's where the derivative of f prime changes sign.
Are we supposed to put like by inspection for all of these?
Yeah, I mean, that's just my little phrase that I kind of made up, but you can just write whatever you want. You can write just by looking at the graph, or you probably don't have to write anything, they just know. I mean, how else are you going to know? Because that's where the derivative of f prime changes sign. You could also instead write, well, that's pretty much good. Questions? Yes?
Wait, so even though it's at prime point P at 2, there's still a POI there?
Yeah, because, yeah. Yeah, it's fine. That's sort of, I know that's kind of in our textbook. Our textbook makes some kind of big deal about this. Actually, the definition of point of inflection is not totally standardized. Like different textbooks kind of do it basically a little bit differently. But it's certainly true that it's concave, because f prime is increasing, it's concave up here and it's concave down here. So yeah, I mean, that's a point of inflection. If it didn't exist there, then maybe it was something. Yeah, don't worry about that. Okay, cool. Now it starts to get a little bit harder. So part C, actually no, C's still kind of easy. It says find all intervals on which the graph of f is concave down and has positive slope. So where f is concave down and has positive slope?
Concave up, positive slope.
Sorry, concave up and positive slope. Can you translate that back into sort of calculus language? Eli, again.
Concave up means f double prime is greater than 0, and that means f prime is increasing. I did one at a time.
Okay.
And then for m or slope is greater than 0, that's when f prime is greater than 0, both of which are by definition.
Yeah. So basically we're looking for places where both the first derivative and second derivative of f are positive. So you can do this just kind of by looking at it. If it makes you feel better, you could make a little chart if that helps you. What was the chart for f double prime? I'm just copying it from like a second ago. There was -4, there was plus, then it was negative, then it was positive, then it was negative. And then what's the chart for f prime? Well, the chart for f prime, just by looking at it, right, it's going to be positive until -3, then it's going to be negative until 1, then it's positive until 4. Is everyone seeing what I'm doing here? So now that I have these nice overlapping number lines, they're basically just saying, hey, when are both of these positive? So you can just look and you can see they're both going to be positive from -5 to -4, and from 1 to 2, and I think that's it, right?
Yes.
You can also just do it directly from the graph. It just
Positive.
means doing more in your head, right? Yeah, where is it positive and increasing? Exactly. Which is kind of how Eli said it. He rephrased it in terms of the first derivative. If the second derivative is positive, an alternative definition for a function being concave up is that f prime is increasing. So you can just look at the graph and you can just do it all at once. When is f prime positive and increasing? Well, it's positive and increasing here on this interval, and it's positive and increasing here on this interval, so it's done. Okay, so do you guys find this like pretty easy? It's like really not that hard, right? You just have to sort of keep everything straight. All right, part D is interesting problem. It says find, basically just says find the absolute max. So find absolute max. Min. Well, find absolute min. Sorry. So how do we find the absolute minimum of a function in general?
Endpoints, relative extrema.
Endpoints and the relative extrema. So yeah, so we should test. Basically, this boils down to two things: test endpoints and test relative minimum. Okay. Well, let's do it. Let's first test the endpoints. And what do we mean by testing the endpoints? I guess I need to figure out what.
Finding if there's something.
Oh, there's a key little tiny thing that they told you almost as an aside, which you practically could have missed, but which is crucially important, which is that f of 1 is 3. So if f of 1 is 3, that's going to somehow play a role in this. So we need to test the endpoints. We need to test what is f of -5. I have to figure out what that is. And I have to figure out what f of 5 is. And where is there a relative minimum?
F equals 1.
In general, f is going to have a relative minimum when the derivative goes from negative to positive. And I'm looking at the derivative. Where does the derivative go from negative to positive?
X equals 1.
At x equals 1, that's it.
And never a critical value.
At x equals 1, that's it. So you should probably write that. You should say f has a relative minimum at x equals 1 because that's where f prime changes from negative to positive. So, since that's the only relative minimum, basically I just need to compare those three values and I just see which one's smallest. Everybody with me? Okay, what is f of, well, one of these is easy, right? What's f of 1?
3.
That's 3. Okay, but the rest of these are kind of tricky. Let's do f of 5 first. This is sort of this is not awkward, but it's a new thing that we haven't really gotten in the habit of writing yet. Exactly. It tells us that f of 1 is 3. So what is f of 5?
Just look at the graph because like that's a slope kind of good.
You don't need to actually get into integer, but it does involve integrals, right? What is f of 5? Okay, there's this sort of expression which just comes up again and again on the AP exam. F of 5 is just f of 1 plus the change in f from 1 to 5.
That's positive.
Which is the integral, right? This is kind of the fundamental theorem of calculus here at work, right? And we know that the fundamental theorem, we know that one way of writing the fundamental theorem of calculus is if you take the integral from 1 to 5 of f prime of x dx, that's f of 5 minus f of 1, right? Say right. Like that is the FTC. That if you take the integral of the rate of change of something, then the answer is the net change. So keeping this in mind, if you just add f of 1 to both sides, we get a new statement which is very similar, which you should also understand, and it should just kind of like roll off the tongue, right? This is the value of f at 1. The integral from 1 to 5 of f prime of x dx represents the change in f from 1 to 5. So this sentence basically just says that f of 5 is just whatever f of 1 is, plus how much f changes from 1 to 5. Okay, does that make sense? Yes?
And based on the picture, you can tell if that's positive.
Based on the picture, you can tell it's positive. It might be worth it to actually just do it, right? F of 1 is 3, and what is the integral from 1 to 5? We can just compute it, right? Isn't it going to be like,
We have the slope, so
it's going to be like something. The slope of this line is -1, I believe, right? Because down 3 over 3. So if the slope of this is -1, then we essentially just need the area of this figure, which is,
1 plus 2 over 2 times.
I think it's just 2.5, right? So it's just 2.5?
3. Somewhere.
Why are you
Might be
dividing?
1/2.
You just divided into two triangles.
I think it's.
That's two triangles. It's like a triangle and a trapezoid.
There's a negative.
Taking the integral from 1 to
5. There's negative.
5. Yeah, oh, sorry. So I just mentally canceled those two out because they're the same.
So it's 1 by
So
1.
I'm just looking for this area, which is a triangle and another triangle and a square. My guys are looking at me like I'm crazy. This is right.
Not
Yeah,
everyone
it's just
mentally cancels.
2.5. Sorry, yeah. This positive area is canceled by this negative area, so I just blew that off. And now, Ingrid, you with me? Integral from 1 to 5. Integral from 1 to 5 is just going to be the same as the integral from 1 to 3 because those two are just the same. And that's like a triangle. That's a square of area 1. That's a square of area half. That's a triangle of area 1 because it's like a half of a 1 by 2. Okay, so this is 3 plus 5 halves. And so the final answer to f of 5 is that it is 11 halves. Okay, now comes the hard one. What is f of negative 5? Well, people are sort of uncomfortable with this at first, but eventually you just get used to it. The one cool way of writing f of negative 5, well, it is also just f of 1 plus
Negative.
yes, or you can even just do it the exact same way, right? You sort of ask the question, some of you wondered, why would we ever put the lower number up at the top? Because you can just write this as f of negative 5 is just f of 1 plus the amount that it changes from 1 to negative 5. That is another kind of key idea, right? That f of negative 5 is just whatever f of 1 is plus the amount that the function changes from 1 to negative 5. But of course, perhaps a more intuitive way to do it is what Eric Chen just said, which is that f of negative 5 is f of 1 minus the amount that it changes from negative 5 to 1. But of course, those are the same thing, right? That's what we do when we switch those two. I think I did that right? Oh, f prime. So basically, whichever way you want to think about it, like this, that's f of 1, and this is f of 1 minus the change from negative 5 to 1. If you prefer to think of the change as being positive, then you're basically saying, all right, take the value at 1, and then subtract how much it changed from negative 5 to 1. That's going to be the value at negative 5. Is this making sense? It's kind of a very intuitive concept on one hand, but it takes some getting used to. Okay, now I just have to compute this. So f of 1 is, of course, 3. And what is the change from negative 5 to 1? Well, that's going to be this semicircle minus that one, right? This semicircle, that has the area of a circle of radius 1 is pi. So that's minus pi over 2 minus, and then the radius of that circle is like 3 halves. Is that right?
But the radius of that circle is 2.
2.
Oh yeah, 2. That's much nicer.
So it'd be pi.
Sorry. Yep. So it would be the area of the circle would be 4 pi, but then divided by 2, so minus 2 pi. So this is going to be just 3 minus 3 pi over 2, which is, something less than. Oh yeah. Oops. Yeah. Minus negative 3 pi over 2, so plus 3 pi over 2.
It's plus a positive or minus a negative, which is still greater.
All right. So by computing the value of f at the endpoints, where is the absolute minimum? Yeah. And note that they say find the absolute minimum value. So they're looking for a particular answer. 3. Right? So you just say, the absolute minimum is 3. So that's kind of like your final answer. And you don't even really have to justify it. If they see that you're computing f at the midpoint, at the endpoints, and also at 1, then you're good. You could also there are also arguably some shortcuts. If you wanted to just argue, you could also, instead of actually computing them, you could just kind of like do it. You could sort of say, well, you could say that f of 1 has to be less than f of 5, for example, because the integral from 1 to 5 is positive of the derivative.
And you can say by
It's
inspection.
positive, so f increases on the interval 1, 5, or the net, I guess you should say increases. So yeah, you could probably just write that, right? If the change in, if the interval from 1 to 5 represents the change in f between 1 and 5, because that's positive, and just like Eli said, by inspection, you are allowed to, I'm pretty sure you're allowed to just look at it and say, by obviousness, the integral from 1 to 5 here is positive, and therefore, from 1 to 5, the overall change is a positive one, and thus, so instead of actually doing it. And you can do a similar thing. You can say, look, f of negative 5 has to be greater than f of 1, or however you want to say it. Why is that true?
So try to get negative.
That's because the integral from negative 5 to 1 is negative, which you can also do just kind of by looking at it. And since the integral from negative 5 to 1 is negative, it means that the function gets smaller overall, and therefore, but you're still, ultimately you're still doing a comparison. It's just whether you actually do it out or you just talk it out. Okay, are we good with this? All right, I think the pages in this packet get progressively harder, but basically if you can do page 1 and 2, you can kind of do anything. All right, you're gonna finish this packet probably like over the weekend or something, so we can put that away. Then there was some bookwork. How'd the bookwork go?
What about the other packet?
The bookwork was hard? Yeah, I thought the last couple were hard. Let's do like say 4 or 5 of
Actually, the
them.
last lady,
168.
160.
Yeah. So this was like section 5. It was all about substitution, right? What were the which were the ones that I assigned like a whole bunch, right? Can we just do like a sampling? Can I see this for a second? Can I see this for a second? Yeah, running just a little bit better. So
168 or 167?
let's do some from the second section. Let's do some of these.
Which ones?
I don't know, which ones seem like good to do?
168 because we're proving a theorem.
Let's do 107, I like that.
The integral and differentiation.
wait, what about 103?
We could do
They
103.
Which 103?
The 103 later, yeah.
Okay, and then how about, let's do like 1 or 2 more from starting where it gets hard.
Some of the last ones.
Some of the last ones.
168 it proves a theorem.
168, okay, we can do that. But
167.
I thought 167 was also kind of tricky. Okay, let's do these. So, okay, 103. 103 was the integral from 1 to 3 of e to the 3 over x squared dx. Okay. So how do we do this? By substitution. I think it's pretty clear here that we should let u be negative 3, or let u be 3 over x. So I'm going to continue to write it kind of as a function because that makes me feel better. So this is 3 over x, otherwise known as 3x to the negative y. So why is that a good idea? Because du will be negative 3x to the negative 2 dx, and that's kind of like what I see here, right? So if I put in a negative 3 and undo the damage with a negative 1/3, then everything is looking good. And this becomes negative 1/3, the integral, the top, or rather, this is basically just e to the u du, right? And now you have to change the limits of integration. So this is u of 3, u of 1. I like to write it out in 2 steps like this. So this is negative 1/3. Integral, if you plug 1 in here, you get 3. And if you plug 3 in here, you get 1 of e to the u du. Everybody with me? Is this how you guys did it?
Yeah.
Okay, and then the negative like flips them back again. So actually it's just 1/3 integral from 1 to 3 of e to the u du. And substitution with integrals is awesome because now we just do it, right? No back substitution is required. And so my final answer is 1/3 e cubed minus e. That's it. Any questions? No, I think I'm right. There's a lot of different places you could make a mistake. I mean, you got to make sure that you take the correct derivative over here and put it in -3. I don't know. All right, let's do another one. 107. Someone asked about 103. Miriam, does that make sense now?
Oh, yeah.
Okay, cool. 107 was kind of tricky. This is the integral from 1 to 2 of x minus 1 root 2 minus x dx. Okay, so by now maybe you're kind of experienced that it makes a lot of sense to let the inside be u, right? So if I let u be 2 minus x, du is negative dx, and so I put in a negative and I undo the damage with another negative. And if u is 2 minus x, then that means that x is 2 minus u. Right? Yes. Which means that x minus 1 is 1 minus u by just subtracting that from both sides. So now I get ready to do the substitution. This becomes a negative. Negative dx makes a du. X minus 1 makes a 1 minus u. So this is 1 minus u root u du. And then here I change this to be u of 1 and u of 2. Everybody following? It's like a lot of things going on all at once. Aaron, you cool? Yeah! So, this u of 1 is 1, and u of 2 is 0. And I can distribute this, right? So this is u to the 1/2 minus u to the 3/2 du. I'm putting it in an anti-differentiation friendly form. And now, I mean, you have a couple of options. It's not really necessary, but some people, this kind of gives them a headache when that number's bigger, so you could just flip it again and get rid of the negative. So the integral, so it's really the integral from 0 to 1 of u to the 1/2 minus u to the 3/2. Is this making sense, everything I'm doing, guys? All right, cool. Now I just do it. Anti-differentiate, so it's 2/3 u to the 3/2 minus 2/5 u to the 5/2, and then they were pretty nice to us, right? Because we just gave us 1 and 0. So this ends up being 2/3 minus 2/5 minus, and then 0 minus 0. So final answer is 2/3 minus 2/5, which is 10 minus 6, so it's 4/15. Where's many of you got the problem right? If you got this right, you pretty much get what's going on. Should we do one more of these kind of basic, like, integration problems? I don't know. Arthi? Someone else? Richard, Luis Paz? John Park? No?
We're still gonna do the last one.
Static, no. What? Oh yeah, I'm still going to do those last two, yeah. So then 167 was a kind of a cool problem, which said prove something. It said prove the following. Prove that the integral from CA to CB of some function is equal to C times the integral from A to B of f of that function. Okay, see for a second. So this is just looks like one of our basic integral properties, which perhaps we could have proven even before we learned about the fundamental theorem of calculus by making like a picture and doing some like crap with like Riemann sums. That's probably possible. But with substitution, I think it's just pretty easy. So let's start with the right-hand side, and I'm going to prove that that equals the left-hand side. And basically, so this is my goal is to prove this. So I'll start with the right-hand side, c times the integral from a to b of f of cx dx. I just make a substitution. Let u be cx. Well, if u is cx, then du is just c dx, which is exactly what I have right here. And now I just change it to a new integral involving u's. So now this is f of u. Fu, guys, anyone who's not, not here today. So c dx is du, and then this is just u of b and u of a. But of course, that just is the thing I'm trying to prove, right? U of b, plugging b in for x, you just get cb, ca, f of u du. And the fact that it's a different variable is irrelevant, right? It's a dummy variable. Oh, sorry, I did bring in the c. I brought it in when I kind of just did it all in one step, right? That's du, so it's just like cool, yeah. Okay, cool. 168 questions about that. It was really not that hard. I think I gave you like 2 that were kind of like that, right? Wait, there was one problem that was like harder.
Maybe 159.
159, yeah. 159 was harder, I thought, than 167. Should we do that?
No.
This was just another kind of a cool problem. It said, show that the integral from 0 to 1 of x squared 1 minus x to the 5th, show that this equals the integral from 0 to 1 of x to the 5th 1 minus x squared. This is not obvious at all. Probably if you, well actually I don't know, yeah, I have no idea how to do, or I have no idea why this should be true. But I think if you do a substitution, it just works out. So let's start, it doesn't matter which side we start with, let's start with the left-hand side. Well, if I just let u be 1 minus x, then du is negative dx. And then I'm going to now just do the integral, right? Put in a negative, undo the damage with the negative on the outside. And now suddenly this gets converted to opposite of the integral from u to 0 to u of 1 of, well, x is now 1 minus u, right? So this is 1 minus u squared u to the 5th du. And finishing this off, yeah, because what is u of 0? U of 0 is 1, and u of 1 is 0. So you flip it, and then you just are exactly here. What's up?
Part B is the same thing.
Oh, there's a part B? Oh yeah, part B, very similar, yeah. Did I assign part A and B? That's kind of me. Sorry, I should have just done one or the other of those. All right, the last one that someone had a question on was 168, which I think is kind of a cool problem. Oh yeah, I think there's a problem in your test like this. 168. Verify that. So first of all, it just says verify, as in don't ask us how we came up with this. Just trust us. No, don't trust us. They're just basically saying, yo, here's this formula. Can you just check that this is actually true? U sine u du.